Good day, everyone. Today we are going to begin our discussion on magnetism. This is the second to last chapter. Both of them are dealing with electricity and magnetism, but today we're going to talk primarily about magnetic fields and how magnets work. So the discussion that we're going to have will be on magnetic forces and magnetic fields. You remember from electricity that we had electric force and electric field. In that case, the electric field was just the electric force divided by the charge. It's a little bit different here, but they are related, and whenever there's a field, there will be a force, particularly on a moving charge, which we'll discuss. Magnets always come with poles. In any magnet system, there will be what we call a North Pole and a South Pole. We could call it positive and negative pole, but because of its application to compasses and navigation, we think in terms of north and south, and we use those names even when we're not talking about north and south per se. So poles are an important aspect of a theory of magnetism. And then we'll talk about magnetic domains, how the electrons in the atoms align themselves to produce a strong magnetic field. Electric currents and magnetic fields, there's interaction we'll talk about, electromagnets, and the rest as we go through. So with that, let's go ahead and get started. Magnetism, it's a term that comes from the name Magnesia, a coastal district in ancient part of Greece. They at that time found these unusual stones that had a property of attracting pieces of iron. They were first fashioned into compasses and used for navigation by the Chinese in the 12th century. The most important place to start on this is to take an iron magnet or magnetized iron and place it on a piece of paper. And what we do is we scatter lightly very small filings of iron that are each consisting of a north and a south pole. And the general pattern that develops is the one that actually shows us what we now call the magnetic field lines. And the magnetic field lines terminate on the poles of the magnet. So you can see that if I were to draw arcs across here from north to south on the upper hemisphere or upper side of this graph, and on the lower side they form arcs, all of which terminate on the north and south, or the ends of the magnet, and which we now call a north pole and a south pole. And the strength of the magnetic field is indicated by the closeness of the lines that are lined between the poles. In other words, we have a higher density of filings near the North Pole, and you see them to be more intense or more concentrated near the poles, and there's fewer filings regions where I'm pointing here midway between the poles, and that is where the magnetic field is the weakest. So the strength of the magnetic field, which will be indicated by its force on a moving charge, is stronger near the poles. First of all, we can say that there is a magnetic force between any pair of magnets. There is a force of attraction or repulsion between them, and it depends on which end of the magnet is held near the other. So in this graph right here, of these pictures I should say, we have the North Pole in closer proximity to the South Pole for this scenario than the South is to the North Pole on the other ends of the magnet. So what dominates here is there's a force of attraction between opposite poles, so opposite sign to the poles. So the force of attraction is similar to electrical forces. The opposite poles will attract each other, and the like sign poles, for example, south and south or north and north, will repel each other. So that's similar to the behavior of electrical forces, where we have opposite charges attracting and like charges repelling. And the strength, we find also the strength of the force between the two magnets depends on how far apart they are. So the further they are apart from each other, the weaker the force, the closer they are, the stronger the force. So that's a summary in a nutshell. As I said earlier, each of these filings can also be considered as a very short, tiny bar magnet, which makes them align their directionality in a way that the south pole of each of the filings is attracted to the north pole here, and over here the north pole of each of the filings is attracted to the south pole. One thing we know is that magnetic poles give rise to magnetic force, and there are two types interacting with each other. One, there is what we call the north pole of a magnet, and what we really mean by that is that it's a north-seeking pole, and the south pole of a magnet is a south-seeking pole. And the rule for magnetic forces between these, the magnetic forces that operates between the magnetic poles is that as we said in the last slide, like poles repel and opposite poles attract. Now, what we mean here by north-seeking and south-seeking, basically this was designed by convention. When people have compasses that point their needles to what we call the north geographic pole, they labeled that point of the end of that needle with an N, meaning that that north pole was actually seeking the physical geographical north pole of the Earth in the Arctic Circle. And a south pole of the magnet would seek the south pole of the compass, which is a bar magnet. Is also a bar magnet. Its south pole is actually south-seeking. This leads to the confusion that what we normally call the north geographic pole is actually the south magnetic pole, and the south geographic pole in Antarctica is actually the north magnetic pole because it is attracting the south pole of a compass, and vice versa. In all magnets, we always have two poles of a magnet. You cannot have one pole existing without the other. This is in contrast to electric charges. With electric charge, I can have a positive charge without a negative charge. Well, I can isolate the two. We said that all matter is originally and by design is neutral because every atom has as much positive charge in the nucleus carried by protons as there are electrons in the atoms that whirl around the nucleus. But when I separate them away, I can separate them by as large distance as I want and isolate a negative charge or a positive charge. Unlike this, I'm not able to isolate a north pole and a south pole. A magnet will always have one end being north and the other end being south. So no single pole exists in nature. A simple ball and bar magnet has poles at the two ends. The horseshoe magnet, bent in a U shape, has poles at the end. And the reason we often or sometimes bend the bar magnet into a U shape is to place the north pole closer to the south pole, and this makes the strength of the magnetic field stronger between the two. The closer the north and south pole come to each other, the stronger is the magnetism or the magnetic force experienced by a moving charged particle, which we'll talk about later. Quick check question for you to think about. A weak and a strong magnet repel each other. The greater repelling force is generated by the stronger magnet, by the weaker magnet. Are they the same, or is it something else? So obviously D will not be one of our considerations, but we can look at this and find and seek an answer to the question of if these two magnets are repelling each other, is the greater repelling force, is it by the stronger magnet, the weaker magnet? Well, the answer turns out to be that they are in fact the same. And the weak and strong magnet repel each other, which is true, but remember Newton's third law, for every action there's an equal and opposite reaction. So the force that the weak magnet on the strong is the same as the strong on the weak. The same is true for, you can think of this in terms of the person standing on the surface of the Earth. The Earth is pulling us towards its center, which causes our force of gravity to be quantified by our weight, how much we weigh when we get on a scale. But at the same time, with the same force, we are attracting the Earth towards our feet. And the reason that force is much more difficult to detect is because the mass of the Earth is so much larger. So we don't really observe the acceleration of the Earth when an object is released off of a cliff, but we do observe the acceleration of the object being released off the cliff as it falls down to Earth because its mass is so much less. The same thing goes here. Pursuing the idea of magnetic fields, we'll examine a little bit of their properties. It's a region of magnetic influence surrounding the poles. In other words, it's that we've seen these field lines originate from the one pole and wrap around into the pole of the other. The shape is revealed by lines that spread from one pole to the other. And these lines are what we observed by filings being laid down on a sheet of paper next to the bar magnet. Now the lines can be visualized by tiny bar magnets called iron filings or shavings, and they align themselves with the magnetic field, and that is why we see the shape of the magnetic field when we scatter these tiny iron filings, which are in fact tiny magnets themselves, over the sheet of paper. So by convention, the direction is from the North Pole to the South Pole. That is to say, the direction of the magnetic field always goes from the North Pole to the South, and it's produced by motions of electric charge in atoms, which we'll talk about a little bit later, but there is a source of this magnetism which is at the atomic level, and it is due to the electric charge, particularly the electron charge, the negative charge, in the atoms. But it is due mostly because of their property called spin, which is similar to the idea of a spinning top, or if I spin a coin on the surface of a table, I have what we call spin angular momentum. Looking at this, we can also say that since the direction of the magnetic field is from the North Pole to the South Pole, that looking at the Earth itself, we said that the magnetic North Pole is at the southern geographic in Antarctica. So the field lines of the Earth come out of Antarctica and wrap around over the top of the surface of the Earth back into the South Pole in the Arctic region, or what we call the northern pole, geographic pole. So anyway, that gives you a way to visualize or understand the directionality of the field. Now, we still not discussed how the field goes into making forces, other than to say that if I have a bar magnet, it will align itself with the magnetic field. And that alignment is used to make use of things like magnetic compasses to give us navigation. We talked briefly about the Earth's magnetic field, but here's a picture of it. In this case, we have the axis of, notice that the spin axis of the Earth is not precisely aligned with the axis of the bar magnet of the Earth. So the way to visualize the magnetic field of the Earth is to think of a giant bar magnet that extends well through the equatorial plane and all the way from the northern top to the southern bottom of the Earth. The exact cause of this, obviously this is not truly a bar magnet, but it is currently believed by most scientists that the cause of this, or what we actually observe as the Earth's magnetic field, is due to circulating charges in the center of the Earth that is generating this field. And because it's so far away, we have no direct way of knowing or actually probing the exact movement of these charges, but that's the way we visualize it. So we can actually now also make another statement that another way to make the same magnetic field as a bar magnet is to generate loops of current that spin around this centralized group of dashed lines going from the top of the Earth to the bottom of the Earth. So we have loops of charges that are circulating to generate this, and this must be due to a liquid core of the Earth which allows the charges to move in a circular fashion so that they're not being constrained to be immobile and thus incapable of generating a magnetic field. How do these magnetic fields become produced in a piece of iron. So iron, as we know, is the property of a magnet. The most common form of a magnet is iron, and it is generally produced by two kinds of electron motion. One, which we will call the main contributor, is the electron spin. So the way to visualize this in atom is that we imagine in this lower drawing where the X is actually where the nucleus or the center of the atom is. It's where the core of protons and neutrons are concentrated. And electrons, indicated by this black circle over here, is moving around, circulating the center. And while it's also circulating about the center, the nucleus, it also is undergoing a rotation of its own axis. Now the electron is charged. We can imagine that it has a distribution of charge as it's spinning, and so these spinning currents of charge will in fact generate a magnetic field. And the reason this arrow is much longer than this arrow is that what it's telling us is that the magnetic field is dominated by the electron spin and not the orbit of the electron around the center, which also forms a current loop and also generates a magnetic field coming out of the center of coming out everywhere, but everywhere within the loop. But the lines come out and then they look just like the field lines of a bar magnet. They come out, divergent, go around, and come back in at the South Pole. This is the picture that we have, and as we said, the field produced by this circulating electron or spin is much more significant from the magnetism point of view than this orbital motion of the electron going around the atom. So the electron spin is the main contributor to magnetism. If I have a pair of electrons spinning in the same direction, then that will create a stronger magnet. But if the pair of electrons are spinning in the opposite direction, then they will cancel each other and the magnetic field will be zero. So in magnetic materials, we've got a lot more of the cases where the electrons are spinning in the same direction, and that's why we see the magnetic properties of iron. Furthermore, it turns out that not all of the iron the spins from all of the electrons in each of the atom don't all point in the same direction everywhere throughout the material, but rather they are broken up into domains which are rather random in their size and in their shape. But within a domain, we find that this is on a microscopic level, very, very small piece of iron, which would be microscopically small, literally as small as the objects seen in a microscope. Within those small domains, the electrons from different atoms and within the same atom are all spinning in the same direction, and they add coherently to make a magnetic field. And each of these blue vectors is due to the sum of the spins of the electrons all spinning in the same direction. So in this case, in this domain, this region of the iron has all of the electrons spinning in a direction pointed by this arrow, whereas over here somewhere else, in this domain, all the electrons are spinning in a different direction. And so generally speaking, if I look at this from the outside world, then everything seems rather random, and the net vectorial addition of all of these adds up to zero, and therefore a piece of iron by itself will not exist by itself as a magnet. However, if I were to place this piece of iron in a strong magnetic field, so I will assume that I have some way of generating a permanent magnetic field, which, as we'll find out, we can do with currents of wire in a system of coils. I can make a uniform magnetic field if I place this iron in there, and if it's strong enough, all of these domains or the vectors will in fact line up in the direction of the magnetic field. So if the magnetic field that I place it in was pointing at an angle of say 30 degrees from the vertical as I am scanning my pointer here, then all of these vectors will line up pointing in the direction of the magnetic field. And when I take that piece of iron out of the magnetic field, it will retain that magnetization. It will not instantaneously go back to this random place, and therefore I've done what I would say is create a permanent magnet by placing these pieces of iron in a much stronger external magnetic field. And then when I remove it, the iron has all of its domains aligned, and therefore the magnetism is observed even after the magnetic field is turned off. There are differences between a permanent magnet and a temporary magnet. In a permanent magnet, the alignment of domains remains once the external field is removed. In a temporary magnet, the alignment of domains returns to their random arrangement once the external magnetic field is removed. And what we find is that in order to create this permanent magnet, we have to add an alloy to the iron so that it is not just a pure piece of iron element, but we add other elements to that help keep all of the domains to be aligned, so that once you remove the magnetic field, the magnet still has a very, very strong effect. Magnetic domains can be described as what we would say is unmagnetized iron, where the vector, the domains all have random orientation. So they're all the same. The electron spins are all lined up and spinning in the same direction within the domain, but from one domain to another they are not. And so I get these regions where I have uniform alignment creating a local magnetic field, but if I look at the magnetism due to the whole piece by that together, then it will not have any significant magnetization. So if I now place it in a magnetic field, I begin to align some of the magnetization within the domains in a direction that tends to be in the direction pointing of the applied magnetic field. And if I increase the magnetic field that I am applying even to a greater extent, then eventually I can get all of these domains to be lined up, and now I will have the strongest magnet possible, because the electron spins from all of the atoms, from all the domains, are all spinning in the same direction, and therefore that makes the magnet as strong as possible. But what's also finally interesting on this slide is that where we might think that by breaking this in half, I can take the South Pole and move it away from the North Pole, and therefore I could actually separate poles as I would with electric charges, but something else happened. When I break it in half, all that happens is that the field lines that were originally going through to the other half are now still pointing in the same direction, but they're coming out into air. And as a result, what happens is this simply becomes the North Pole of the magnet that complements the South Pole. And similarly on this end, where I had only the North Pole, I've now created a South Pole, because by breaking it in half, all the field lines at that end are pointing interiorly towards the North Pole. And so basically breaking a dipole, a bar magnet in half, simply makes two bar magnets, each having a North and a South Pole. Okay, I think we'll stop there for this lecture so we can resume on the next one, and everyone can take a break.